Now I want to take a moment to step away from greatest common divisors in the Euclidean algorithm because something really cool and fundamentally algebraic was going on the previous slide that I just can't stop talking about. And what that is the concept of prime power factorization. Because honestly, prime power factorization is really, really cool. So there's a theorem called the Fundamental Theorem of Arithmetic. And you know when there is the fundamental theorem of in the title of a theorem, that is a super all-encompassing important theorem. And that theorem, the Fundamental Theorem of Arithmetic, states that if you have a positive integer that is greater than 1, it can be represented as a product of primes in a unique way, almost, up to rearrangement of the terms. And I want to take a moment to talk about two things here that are really interesting in that theorem. And both of these things will come up again in abstract algebra, and they come up universally more in a lot of mathematics. So what about that up to rearrangement of the terms part? Why is it unique way up to this sort of thing? Well, we know that the order in which you multiply numbers doesn't fundamentally change the answer. So if I use the example of 396 that we were using in the previous video, it's true that I could write that number as 2 times 2 times 3 times 3 times 11, where the primes, 2 copies of 2, 2 copies of 3, and 1 copy of 11, those primes are going to be unique, as is the number of times that they occur. However, I could shuffle the order, and instead of thinking of 396 in this sort of ascending order, 2, 2, 3, 3, 11, I could write it as 11 times 2 times 3 times 3 times 2. Or I could write it as 11 times 3 times 2 times 3 times 2. There are many different ways that I could rearrange those terms, change the order in which I'm multiplying, and the answer would be the same. So what is unique about this is the primes that occur. There's no way to take 396 and write it with a prime factor of 5, for example. So the fact that you have 2s and 3s and 11s and you'll never get any other primes, that's a guarantee by the Fundamental Theorem of Arithmetic. As is the number of times each one of those terms appears. So the fact that there are 2 3s is also fundamental. There's no other way to take 396 and somehow write it as a product of 3 3s along with other copies of 2 and 11. So other than just shuffling up the order in which we're multiplying, the way in which we decompose this number as a product of primes, the primes that occur, the number of times they occur, those are all unique. So if you wanted to say, obviously I meant this way, obviously write it in terms of the 2s first and then the 3s and then any 5s should they occur and any 7s should they occur and so on. If you fix an ordering that seems natural to you in which you're going to multiply or write that decomposition, then it becomes unique. So you often quote the Fundamental Theorem of Arithmetic as saying, every positive integer greater than 1, which is also important, can be written as a product of prime powers in a unique way, assuming that we're fixing that ordering. Now the other thing that's super exciting about this theorem is the n greater than 1 part. Sometimes, especially if you're speaking with non-mathematicians, they'll ask you, isn't 1 a prime number? Because remember, the definition of a prime number is a number that's divisible only by 1 and itself. So it really seems like from that definition that 1 ought to be a prime number. And the fact that 1 is not a prime number, that was unclear. Historically, mathematicians used to argue about whether or not 1 should be a prime number. And the thing that finally won the battle and said 1 should not be a prime number is the Fundamental Theorem of Arithmetic. If we allowed 1 to be a prime number, then the number of times the number 1 appeared in this decomposition would no longer be unique. For example, I could write 396 as 1 times 2 times 2 times 3 times 3 times 11, Or I could write it as 1 times 1 times 1 times 2 times 2 times 3 times 3 times 11. So I could have 1 appearing any number of times. And this unique prime power factorization that the fundamental theorem of arithmetic gives us would have to go away if 1 were a prime number. We wouldn't be able to say that anymore. The number of times that 1 appears in the decomposition would be variable and changing. And that thought was so appalling to people that they decided that 1 should not be a prime number. So this theorem is a super important theorem. The fact that we can take all positive integers greater than 1 and decompose them in this way is what makes prime numbers almost holy to number theorists, and is the reason that 1 is not considered a prime number. And because I think that's just so cool, I had to take a whole video just to talk about it. So in the next video, we'll get back to greatest common divisors and the Euclidean algorithm as promised, but this theorem, super important theorem, very algebraic at heart, and very interesting history.